All right, welcome to our third day recap. So remember, every single day, or almost every day, we're going to do a little bit about changes. Today was the first day we met in the different class on Tuesday in ECG 237, and of course we had a lot of problems with the technology. I did. And so eventually I emailed all of you this table. And I asked you to look at it and look at the three values that came from these problems from yesterday and try to come up with names for what they all were. And so I gave you about 5 minutes, so if you want to pause and do this for yourself, now is the time to do it. And so in the end, I was very happy to see that most people were able to identify these three kind of categories to which all of these other values for almost every single problem, or every single problem rather, belong to. There is the initial value, there's the final value, and there's the change. For example, Alice had 7 cakes today. Today she has 12 cakes. What's the change? Plus, why is this not writing? Plus 5 cakes. Shelley's cat weighed 17 pounds. Then her weight changed by 6 pounds. Now she is 23. The rat weighed 12 ounces. Then his weight changed by -3. So now he's 9. Andy changed his sausages by -5 and he had 18. He must have started at 23. And so the change is 4. And when Cameron began, we want to figure out what the initial is. At the end, it had 6, and so it had to start with 2. Perfect. We also did how they relate. So let me actually get us a blank sheet with which to do this. Alright, so we do have initial, final, and change, which I asked you to use delta at the time, but now I'm going to ask you to use this D. So if I have the initial and the final, how do I get the delta? If I have the initial and the change, how do I get the final? And if I have the final and the initial, how do I get the change? Final and the delta, how do I get the initial? Whoa. And I gave you a few minutes to come up with that in class. So here are the answers. If I want the change, I have the final minus the initial, and that's the change, right? Because that's by how much more is F, the final amount, bigger than I, the initial amount. If I have the initial amount and I have the change, if I add them together, you will get the final. And if I want the initial and I have the final and the change, well, I have to take the final and then say, well, I have to take off what happened and get the initial. Now, of course, all of these, you can write one and then you can algebraically solve for the other two, right, just by solving for something. And you can check yourself to see that that's true. But it also should be very common sense that that's how an initial value, a final value, and a change in values are all related together. Alright, now I'm going to clear this, and we're going to move on to our next shift. Going from variables stand for unknowns to variables vary. So I started off with this question. I asked everybody, does a variable like X vary? Sorry about my handwriting, I'm still working on this. And everybody gave a resounding yes. Yay. Yes, absolutely. Alright, and I asked, are you sure? Does that mean that X varies across all the real numbers? Everybody nodded, they shook their heads yes. And so then I asked you guys to answer the following question. X plus 3 equals 5. I gave you a second. And then I said, all right, guys, what do you think? And everybody, and I think this is where I first started Poor Man's Clicker, where I yell 1, 2, 3, and everyone yells their answer 1, 2, 3, 2. Everybody had 2. X equals 2. And I said, all right, well, is x equal to 4? Is this true? Oh, people said no. Is x equal to 0? Nope. Is x equal to negative 0.48395? Question, is it? And people said no. All right, well then where's the variation? If on this whole number line, the only thing that x can be is 2, right here, I don't see any variation along the number line. How can you reconcile those two ideas? How can you reconcile the fact that you said that x does vary with over here, the fact that you said x equals 2? And we talked about it for a little, and I asked people what their thoughts were. Some people said, well, it can vary in different equations. And I said, well, how can it vary in this equation? I'll go ahead and tell you, it does vary inside this equation. How can that be true? And after we had a little more discussion, I said, all right, let me give you a hint. I'm going to give you a visualization of exactly how x does vary inside this equation right here. Because x, if we use x as a variable, it should always vary. And so I gave you this, and I asked you all to look at it. You also downloaded this onto your laptops and shared with those that don't have laptops. And I gave you a few seconds to play it and talk about it. And I heard some good conversations, because if you notice, x is varying, isn't it? X is covering, just like we talked about earlier in shift 3, going from thinking about whole numbers to all real numbers. X is covering every single possible value. So how can this be true? And then we had a little discussion about it. And with people building onto other people's ideas, we didn't have one person give an entire idea. We came to the conclusion that x does vary through all the real numbers. Whoa. All the real numbers. But, so what's special about 2? Only x equals 2 makes the equation balanced or true. In other words, when we write x equals 2, when we write x equals 2, we're not freezing x right here, okay? We're still, come on. We're still letting this animation happen. We're still letting x go through every single value. But it's only x equals 2 that makes this equation balanced. And therefore, 2 is not the only value of x. Instead, we need to rethink what that answer is, right? What we sometimes just call an answer. 2, or x equals 2, is the solution because it makes the equation true or balanced. But x still varies throughout every single value on the real number line. And so then we decided to go over these different vocabulary words. All right, from now on, we're going to use variable to mean a symbol that represents a varying value. A parameter is a symbol that represents, and I asked people to give me some answers because they had read the book, that represents a situational content, a situational constant. In other words, a constant in one situation. It can be known or unknown. And then a constant is a number that doesn't change. A number that never changes value. And so I want to give a more clear understanding of what the difference between variable and parameters. If you notice, both variables and parameters are letters or symbols, right? Oh. Constants are 3 or pi, or e, or square root of 2. So what's the difference between a variable and a parameter? I'm going to actually go to the book for this. So in a second I'm going to go ahead, actually now I'm going to go ahead and clear these answers. So we have the situation where the length and the width can change, but the fence length remains the same. And so what if I define some letters here? Because remember, variables and parameters are not the varying or constant quantities, they are the symbols. They are the letters or symbols. Right here, if I were to define some letters, let's look at area of the rectangle. Let's look at L for the length of the rectangle, the width, and the perimeter. So which of these are parameters and which ones are variables? So I'll give you a second. You might want to pause. Okay, so let's look at this. Well, in this situation, which one of these have varying quantities and which one of them have the same quantity throughout the situation? Throughout the situation, we see that area changes, right? We can see it right here. We see that length changes. We see that width changes. But we also see that the perimeter of the fence never changes. That means that the area, the length, and the width are all variables. Why? Because they represent varying quantities. In contrast, the perimeter is a parameter because it is at a constant 240 meters, right, throughout this situation, in this situation only. Is the perimeter in every situation you will ever come across ever 240 meters constantly? Nope. That's why this is not a constant. P is a parameter, a situational constant that remains steady throughout this one problem. One way I like to think about it is imagining a movie. A variable is going to change within the movie. A parameter stays with one value throughout the movie, but it might have a different value in another movie. And notice that this can be known, right? In this case, we know the parameter's value is 240, or it can be unknown. Maybe I didn't tell you what the perimeter was, but if I label something P for perimeter, it's still going to be a parameter because it doesn't change in this situation. All right, I'm going to clear these notes. And let's finish up what we did on Tuesday, the 23rd. So we ended with a couple of examples from Chapter 1 so that then you could go home and do the homework. Here's one example from Chapter 1. The volume of an average-sized human body is 66.4 liters, which is 0.0664 meters cubed, and the volume of a human cell is 1.1 e negative 15 meters cubed. How many cells are there in an average-sized human body? All right, so I want to ask, when I'm asking this, the number of cells in an average-sized human body, it's really asking me how many cells fit into a human body. Well, what if I asked you how many 3s fit into a 6? What would you do? Well, let me put question marks at the end. How many 3s fit into a 6? Oh, that's 6 divided by 3. Remember, you can write equals 2, but you don't have to write it. This alone, this 6 over 3, already represents how many 3s fit into a 6. So how many cells fit into a human body? Well, let's do that problem now. Here is the size of a human body, 0.0664 meters cubed. Here is the size of an average human cell, 1.1 times, don't use x for times, it looks too much like the variable. Do a giant dot or a star or parentheses, times 10 to the negative 15 meters per cube. If I divide these, they say how many cells fit into a human body. Here is the answer to this problem. Come on. You can calculate that out, but this is good enough. In fact, it's more helpful. It shows me exactly how you got this by saying, oh, I have to divide the size of the thing I'm measuring, right? You're measuring this by the size of the thing I'm measuring with. How many cells fit into a human body? I'm going to clear these answers. And let's do our last example. So we're given the speed of light. Here is the speed of light. We're given the distance to the sun. How many minutes will it take a pulse of light to travel from the sun to the earth? Okay, so here's the distance of the sun in kilometers. I notice the speed of the light is in meters per second, so I'm going to go ahead and get my distance in meters. So 149,597 870.7, this is kilometers to the sun. If I multiply by 1,000, oops, this is now meters to sun, right? Because there's going to be 1,000 more times more meters to the sun than kilometers to the sun. All right, now I look at, well, how many times does this amount right here fit into there? This many meters. Because that amount of meters takes 1 second. So twice that amount of meters will take 2 seconds, and so on. So if I divide by this, divide by 299,792, this now, let me circle all this. Whee. This represents how many chunks of 299,792,458 meters there are in 149,597,870.7 meters, right? Okay. Now, if that's how many chunks there are, well then how long will it take it to go this far? Well, each of these chunks takes 1 second. So this is also, do I have another color? Yes, I do. So this is also equal to the number of seconds light takes. Alright, and let me review that one more time. I know that this amount of meters takes 1 second. So if I figure out how many of these amounts of distance fit into this amount of distance, then that many chunks of this distance will take that many chunks of seconds. So this is now equal to the number of seconds that light takes to go from the sun to the earth, but it did ask me how many minutes. So what I need to do is take this entire thing. Usually I'd write under here. I don't like using the slash, but because we are running out of room, it's going to take, divide this whole thing by 60. And now this is the number of minutes light takes to travel from sun to earth. This entire thing. The blue quantity divided by the red quantity, and all of that divided by the black quantity. Alright, so this is all we had time for on Tuesday, 8/23, day 3. I will join you in a second for our recap of day 4.